In this video, we'll discuss what is continuity equation and its application in fluid dynamics. Continuity equation is derived from the concept of conservation of mass. That is, mass can neither be created nor destroyed. The continuity equation states that in a steady state system, the mass entering the system is equal to the mass exiting from the system. That means if we look at the system with the mass entering from section 1 and exiting from section 2, the amount of mass entering this in the system should be equal to mass exiting from the system, right? So what is mass? Mass is density times area times velocity, right? So density times area times velocity. That means m1 mass at 1 should be mass at 2, because density is same, because we are using the same fluid. Whatever fluid enters here, the same fluid is going to exit, which means density at section 1 and density at section 2 will be the same, which basically means area 1 times V1 equals to area times V2. Okay, so this is basically the continuity equation. Now, the same principle is applied in branch pipe as well. In this case, the flow enters in section 1 and flow exits from section 2 and section 3, which means flow entering from section 1 should be equal to flow exiting from section 2 and 3 sum. The addition of the flow exiting from section 2 and section 3 should be same as whatever is entering in the system, which is Q1. Let's look at an example here. Water flows constantly across two cross sections, cross section 1 and cross section 2, in a long straight pipe with uniform cross sectional area of 0.1 meter square. So the cross sectional area is 0.1 meter square at both sections and throughout. If the velocity of water at section 2 is 3.5 meter per second, what is the velocity at section 1, right? So discharge equals to A times V, Q1, discharge at section 1 equals to discharge at section 2. That means A1 V1 equals to A2 V2. And if we know that both sections are similar, that means V1 equals to V2, which also means V1 also has to be 3.5. So the velocity at section 1 should also be the same, which is 3.5 meter per second. Now, second part of the question, what will happen if area at the section 1 is 0.1 meter square and at the section 2 is 0.2 meter square? So instead of having a constant section, the sections are different, right? So section 1 is 0.1 meter square and section 2 is double of that. Again, apply the same equation. Discharge has to be, regardless of the size of the section, discharge has to be the same. Q1 equals to Q2, which means 0.1 times V1 equals to 0.2 times 3.5, and this gives us velocity is 7 meter per second. So we can see decrease in area will increase the flow velocity, as the same amount of volume has to pass from the smaller area, because volume is constant, but if you decrease the area, then you need to increase the velocity, and the opposite.